In this video, we're going to be looking at the vector nature of rotation. And what we're going to find is that there are a ton of similarities between the vectors that we do in translation, which is everything that you've been doing so far this year, and then vectors in rotation. But there is going to be one little difference. And so we're going to have to start thinking in 3 dimensions instead of just the 2 that we're familiar with. Now, I want to start by saying that in terms of assigning positive and negative values, just follow the rule that clockwise is going to be negative and counterclockwise is positive. And you can't really go wrong with that. But that's not actually the direction that the vectors point, okay? For example, you may be inclined to believe that if we have this wheel rotating, we'll just say in this counterclockwise direction, and you had to represent that with an arrow, with a vector, okay, a hand-drawn vector, how would you represent that? Would you pick just a point on the edge of the wheel, like maybe out here, and then draw a vector that points this way? Or would you do it over here and draw a vector that points that way? Or perhaps you would just draw a vector that goes in a circle like this. What would you do? Now, for myself personally, I struggled with this in the beginning until I got used to it. I was inclined to want to draw an arrow that was not a straight arrow. But that presents a problem for us, because what happens when you want to do a head-to-tail vector addition? You know, head to tail, you have 2 vectors, vector A plus vector B, and that leaves you with vector C. But how do you do that when the arrows are pointing in circles? If you just pick one point on the edge of the wheel, all you're looking at is the tangential component. So if you remember what we did with circular motion, we had the RTZ coordinate system. All we're looking is at a point in space, at a point in time, and looking at that tangential component, but that really doesn't accurately describe what's going on with this rotating wheel. And certainly, whenever we look at this perspective here, where we try to draw our vector as a circular shape, the issue we run into is what happens whenever you're greater than 2 pi radians of rotation. You know, maybe the angular displacement is 100 pi radians. So do you just keep going with it like this, right? And then finally you get your 100 pi radians or 200 pi radians and we're done? Okay, so obviously this is going to create some challenges. And that is not the way we tend to think of our rotational vectors. So in order to resolve this conflict, what we're going to have to do is change our way of thinking a little bit. And the way this works is the right-hand rule. And the right-hand rule has you use your right hand, and if this wheel is rotating in this counterclockwise direction, then your hand will be positioned like this. There's your thumb, and there's your 4 fingers. And what you're going to do is you're going to curl your fingers in the direction that the wheel is rotating, and your thumb is going to point in the direction of the vector. So this is going to be 3-dimensional. It's not really easy for me. I'm not an artist, so I have a hard time drawing what this is supposed to look like. But if you can imagine, you just wrap the fingers of your right hand in that direction, and your thumb is going to point out of the screen that you're viewing. Okay, and that would be the direction of the vector. So what I have here is this wheel. It's rotating in the counterclockwise direction, and this is looking at it from the side. But what we're going to do is rotate it so we're looking at it from the front. And this line here represents the axle that the wheel is spinning on, and the top of the wheel is pointing. It's rotating in your direction, and the bottom of the wheel is going into the page. So it comes out of the page on the top and it goes into the page on the bottom, V tangential. Okay, it's out of the page on the top, into the page on the bottom, and at this point right here, at this point right here, the tangential velocity would be pointing straight down. Okay, so what's going to happen is your fingers are going to be curled towards you, but your thumb is going to be pointing in that direction. And that's the important thing to take note of. Now, if the wheel were to rotate in the other direction, then your thumb would point in this direction. So here's the general rule whenever we're dealing with rotational quantities. The vectors will always point perpendicular to the plane of motion. Okay, so what I mean by that is this wheel is rotating in the plane which is parallel to your screen. So the vector is going to be the reaction to that plane, and it's going to be pointing perpendicular to it. So we have an action which occurs in the plane, and the reaction is perpendicular to it. Now, this is important because remember, what about the case where you want to draw your vector where it's just a circle that goes around 4, 5, 10, 100 times to represent what's happening in your particular situation? In other words, we've got 10 pi radians or 100 pi radians worth of rotation. So how do you represent that in that particular paradigm? And the answer is you don't. So we turn to these straight line vectors. In other words, the vector is parallel to the axle or parallel to the axis of rotation. The wheel, the reference line for the wheel is right here. So we'll make this the reference line. So this is 0 radians as our starting point. And let's just go with this position right up here, and we know that that's going to be pi over 2 radians. So my position vector is going to start. Now I'm going to make the origin the center of my wheel, but it doesn't have to be. It's a vector. Remember, we can pull it out and put it anywhere we want. In fact, maybe I should do that. So my vector is going to point pi over 2 radians in that direction. Now if I continue to rotate that wheel and I go to pi radians, which is right there, then my vector is now going to point, the position vector is going to point to pi over 2. So not to overlap these, I'll do it like this. And pi over 2 is going to be this. So what's my displacement? Well, remember that displacement is final position minus the initial position. And so my displacement is going to be this. It's going to go from where I start to where I end. This ends up being the displacement. Okay. In terms of the angular velocity, we do the exact same thing. Nothing has really changed here. So if I want to represent the angular velocity, allow me to use a different color for angular velocity. The wheel might be rotating at 10 radians per second, and maybe this line, this arrow, represents 10 radians per second. If the wheel then speeds up so that it's going 20 radians per second, then I have an arrow which is twice as long. And if I do V final minus V initial divided by T, which in this case, because we're talking about rotation, it's not V final minus V initial, but it's omega final minus omega initial divided by T, then what we're going to get is that the acceleration vector goes from where we started to where we ended, and that would represent our acceleration. Okay, so this is the weird vector nature of rotational variables. Okay, it's always perpendicular to the plane of interaction. And if you have a hard time understanding it, that's okay. Okay, I don't fully understand how to conceptualize why it has to be that way. I made the mistake once, many years ago, of talking to somebody who was smart enough to apparently understand why the vector actually points in the direction that it does. And after about 10 or 15 seconds of him trying to explain it to me, my eyes started doing circles in my head, and I had no idea what he was saying. And so I've come to this conclusion. That is that if somebody is smart enough to explain why and visualize why a rotational vector is perpendicular to the plane, consistent with our right-hand rule, they're too smart to explain it to an average person like us. So take that for what it's worth. You just kind of have to accept it. Now, in terms of making sure that everything is consistent with what we've set up here, that is that the clockwise direction is negative and the counterclockwise direction is positive, we just want to make sure everything is consistent. So let's explain how that works. If you look at this as an XY axis, either one of these drawings, so basically we'll say that we have X is going to be in this direction, horizontal, Y is in that direction, and if we go into 3 dimensions, we have the Z axis, which would look something like this. All right, so with this view here, this would be our X direction, this would be our Y direction, just like we expect. And if we rotate this wheel around so that we're looking at it in this view that I've drawn here, then what we have is Y is in this direction, X is going straight into and out of the board, so it's going in and out perpendicular to your screen, and then this direction becomes the Z direction. Okay, so we're just looking in 3D. All right, now we know that up is positive, to the right is positive, and out of the screen is positive. So on the Z-axis, this would be the positive direction. So what we have, if we use our right-hand rule, remember that the wheel is rotating so that the front of this looks like it's going in the down direction. Okay, so the front of that wheel looks like it's going down. Using our right-hand rule, the positive Z-axis is going to the right in this diagram here on our right. And so that means this is the positive direction. We've already established with the right-hand rule that these vectors here represent, well, this was theta here, theta initial, this was theta final, this was delta theta, and this is omega initial, this was omega final, and this was delta omega. Okay, so this is the positive direction here. This is plus Z. Okay, and we got that because the wheel was rotating counterclockwise. So counterclockwise means the vector points in the positive Z direction. Clockwise would make it just the opposite of that.